Hello everyone, my name is Mircea Lazar and I'm recording this presentation based on the slides that I use at the Koopman operator workshop in Cres in Croatia. Apparently there has been some technical fault, so my live recording presentation didn't have a video, and I thought it's better if I record my presentation live on the same slides. In this talk, I will recall the Koopman operator preliminaries and problem setting for discrete time nonlinear systems that are more specific to the approach that we will use. Then I will discuss a novel generalization of the Koopman operator via tensor product of Hilbert spaces, and I will show how this leads to a new learning architecture and data-driven approximation methods. Finally, I will point out some interesting aspects how from the generalized Koopman operator we can derive a so-called nonlinear fundamental lemma, and I will end with conclusions and outlook. So first, to consider the setting we are in, we consider a discrete time nonlinear system where x takes value in a subset of Rn, and there is a map, capital F, which transfer the state at time t to the state at time t plus 1. There are no inputs. This map is unknown, linear, possibly continuous. Usually, one of the approach that you take in the Koopman operator is to introduce the Hilbert space that is defined as the set of Lebesgue measurable functions on x with measure mu x, which we call for brevity the L2 space with the usual inner product. Then the next step is to define observable functions, which are real or complex valued functions that belong to this L2 space, which is defined for the state. And then these observables are stacked into a vector, and we can add infinitely many observables, and this creates a new coordinate, capital phi x, which can move, let's say, between these L2 spaces. Now the Koopman operator is defined as an operator that acts on each of these individual observables that belongs to L2 or Hx, and it's a composition operator, so it basically propagates the state forward in time in the lifted coordinates. This is the equations that are typically used, where calligraphic K denotes the Koopman operator, and Z denotes the lifted state at time t, and Zt plus 1 denotes the lifted state at time t plus 1. There are several ways that you can take to prove the existence of the operator. The method that we will use in this work is the orthonormal basis expansion in Hilbert spaces, and this comes from the recent paper by Professor Asada. In this approach, you take the observable functions phi I, x as an orthonormal basis that spans the L2 space on the state, and then you make the typical assumption that the composition of the observable functions with the system map F remains in L2. This is a mild assumption. For example, if we have mappings with compact support that are continuous, this is true. And then the Koopman operator can be analytically constructed of the product of this matrix Qx, which contains these inner products, and the inverse gram operator Rx, which is the gram operator with respect to the basis. And if this is an orthonormal basis, then the gram operator is invertible, so we can construct the Koopman operator in this fashion. The advantage that we get is, compared to the original system dynamics, which are nonlinear and complex to analyze, in this case we end up with an infinite dimensional but linear system for which we can analyze stability or other properties. The learning architecture also comes naturally from the way how we build the Koopman operator. In this case, we can see this observable function as a lifting that takes the state at time t and creates the infinite dimensional state vector phi x, where each component belongs to the L2 space Hx, and then the Koopman operator acts on these individual observables and maps them into the L2 space again. And if we want to retrieve the original state, then we need a so-called decoder which inverts phi of x and retrieves x at time t plus 1. This is typically the Koopman operator learning architecture, and the only difference is the choice of observables, which will be discussed later. Now the problem that we consider in this talk is what happens when we have a discrete time nonlinear system with inputs. So the mapping F now depends not only on the state x of t, but also on an exogenous, typically control input u of t, which belongs into a subset of Rm. We see that the mapping is defined on x Cartesian product u and takes values in x. And the question is, how should we construct the domain of the Koopman operator in this case? We see that for the next state at time t plus 1, we can still use the state observable phi x, but for the observables that mix xt and u of t, there is multiple options we could explore, and I will mention some of them that have been presented in the literature. One of the initial options that can be found in the paper by Proctor and others is to stack the state and the input into a vector and to define the observable functions on this stacked vector space. Then you could create an artificial autonomous system where the u is no longer an exogenous input, and the Koopman operator could be defined in a similar way as for systems without inputs. Another approach proposed by Korda and Mesic is to exploit the input-affine structure of the map F in case it has such a structure. In this case, you could lift the states separately, and then you could use a linear operator of the input, and then you create this stacked space where you have lifted states and products of lifted states with inputs, and this is the so-called linear in control or bilinear in control form of the Koopman operator, which is one of the most utilized currently. Yet another approach, which is relevant for the approach that we'll present today, is to consider the input as a parameter. This was proposed originally by Williams, and more recently Guo and co-authors have reconsidered this approach, and in this way the Koopman operator is no longer a linear static operator, but it depends on the input and it multiplies the state observables. So overall, if we can make let's say an overview of the existing methods, and I only mentioned a few examples that are characteristics to many of the approaches. For a complete overview, I refer the interested viewer to this excellent survey papers. So what we can conclude is that for system with inputs, there exists a diverse non-minimal dictionary observable functions, which can be stacked together and mixed as you like. But there are some open questions which, to the best of our knowledge, have not been completely answered. One of them is, what should be the topology of the Koopman operator domain? How should we construct this lifted Hilbert space on which the observable functions are defined for systems with inputs? Can we derive necessary and sufficient conditions for completeness, meaning that our parametrization converges? Does there exist a minimal complete dictionary of observables that suffices to be employed? And our aim in this talk is to answer the underlying questions to all of these questions, which is, what is the natural generalization of the Koopman operator to systems with inputs? The idea that I will propose is to generalize the Koopman operator to system with inputs by tensor product of Hilbert spaces, and next I will show how we can do that. So we consider again a discrete time nonlinear system with inputs, where the map F depends now on both x of t and u of t, and similarly as Professor Asada has done for system without inputs, we define Hilbert spaces on X as an L2 space, and also a Hilbert space on U as an L2 space on the space of inputs, both with the usual inner product. And similarly, as we have defined state observable functions, we now define corresponding input observable functions, where each input observable function belongs to the L2 input space HU. Now, the same as we did for the case without inputs, we take these observables, the state observables and the input observables respectively, and we stack them together into two big vectors, and we can stop an infinite amount of these observables. And what we will do next is we will define the domain of each of these observables as of the Koopman operator, as the tensor product between the L2 space of state observables and the L2 space of input observables, or Hx tensor product Hu. And this is a product Hilbert space gives us, and the Koopman operator can now be applied to each individual observable in this space, and it can produce a new state which corresponds to the L2 space of the lifted state. So in a compact notation, we see that we can construct an infinite dimensional linear operator K, which acts on the tensor product between lifted states and lifted inputs and produces the lifted state at the next time instant. And we see that we have the same parametrization as for systems without inputs, only that additionally we have that the inputs are lifted via suitable input observable functions. Now, the key assumptions that we employ, and we show the existence of the generalized Koopman operators, are that the system of state observable functions and the system of input observable functions respectively form Ritz bases in their corresponding Hilbert spaces Hx and Hu. And we adopt the natural assumption that the composition of the state observable function with the system map F belongs to the tensor product of the state Hilbert space and the input Hilbert space, which is itself a Hilbert space denoted by H. Just a refresher, a Ritz basis is a generalization of an orthonormal basis, which is the transformation of an orthonormal basis via a bounded and bijective linear operator T, and it was introduced by the Hungarian mathematician Frigyes Ritz, and it has some very nice properties that I will outline in what follows. So based on the construction, we can prove that the generalized Koopman operator can be written as the product of these two matrices, Qx, which shows how the function f is encoded in the product basis psi, and the inverse gram operator of the product basis. And the nice thing is that we obtain this product basis simply by taking the product basis of the state basis and input basis. So basically, it suffices if the input observable functions and the state observable functions form Ritz bases in their constituent spaces, and then the tensor product will automatically yield a Ritz basis in the tensor product of the two Hilbert spaces. Why is this important? Is that because if you like to do a function expansion in a Hilbert space, then the gram operator in that basis is invertible if and only if that basis is a Ritz basis. So this gives us necessary and sufficient condition for the existence of the Koopman operator, and it shows that we are not introducing any conservatism by assuming that the set of observable functions form Ritz bases. Next, given this construction, let us have a look and see what does this tell us in terms of the learning architecture that fits the generalized Koopman operator, and what does this imply for the data-driven approximation methods that are typically employed to construct Koopman operators approximations from data. So as we discussed for the autonomous case in the system with inputs case, similarly it holds that the construction of the domain of the Hilbert space H is naturally inducing the learning architecture. So in our case, we have this independent lifting of the state space via state observables and the lifting of the input space via the input observables. And we see that this is also advantageous in a data-driven context because we can sample the two spaces completely independently, which is not the case when these two vectors are stacked in a joint space. And afterwards, we perform the tensor product, and this gives us a set of observable functions where each observable belongs to the tensor product of the state and input Hilbert space. And then the Koopman operator, the generalized Koopman operator for system with inputs, acts on each individual observable in this vector and produces a state in the Hilbert space of states, so the lifted state space. And then similarly as for the autonomous case, we can use a decoder and reconstruct the original state at time t+1. And this gives us the generalized Koopman operator learning architecture. And what we can see is that if we remove the input, then there is no more tensor product, and we naturally recover the original Koopman operator for system without inputs. So this shows to us that this is a natural generalization. Also, a sign of a good generalization is that it can be further generalized with ease. For example, if we have systems that admit additional independent inputs like disturbances or interconnection with other systems in a network, then we can add a third input with a third space, lift it with its own corresponding Ritz basis, and then form a tensor product with the already tensor product space of states and inputs, and then we will have similarly a generalized Koopman operator that can deal with finitely many independent input variables. So this shows that this is a natural generalization as it can go up or down in the complexity of input variables that you can account for. Now let us see what happens if we try to use this new learning architecture for data-driven approximation of the generalized Koopman operator. So typically, if you consider a discrete time nonlinear system with inputs, what is currently done is that we take trajectories, a series of states that depend on time of inputs, and series of states shifted one step ahead in time. Then each of these are lifted to give us the matrix Zx, which consists of the sequence of lifted states. The same we do for the inputs, and we have a matrix Vu of lifted inputs, and we can obtain the matrix Zx plus just by shifting by one time instant the lifted states. And one of the most popular approaches for approximating Cooper operators from data, called the extended dynamic mode decomposition approach, would, for example, in this case, if we consider independent observables for input and states, try to compute some matrices AB such that this additive structure fits the data. So you have a model that's linear in the lifted input or in the original input, or many variations of this exist. But the point is that in the EMD approach, the standard approach for system with inputs, you can see that the space is composed by stacking lifted states and inputs. And this is not necessarily complete because just summing up or stacking Ritz basis does not give you a Ritz basis in the lifted space necessarily, and we know that's a necessary condition for completeness. Instead, we can see that the structure that we proposed for the generalized Koopman operator can be compactly written as the Khatri-Rao product of the matrices Zx and Vu, where this Khatri-Rao product essentially means the Kronecker product for the columns of these two matrices, and the Kronecker product just implements the tensor product in a finite dimensional case. And we see now that the Koopman operator acts on these Kronecker products, which form a Ritz basis as you take things up to infinity, and achieves completeness compared to the standard ND approach. Also, it comes with some numerical advantages because singular value decomposition of Khatri-Rao tensor products can be performed efficiently. One important observation is that I would like to make is that you can still employ a non-minimal Koopman embedding. So establishing completeness of the tensor product does not stop you from using one of your favorite linear plus bilinear terms Koopman representation, where also original states and inputs can be added to the observables. But the key message that we give in this work is that it is a necessary condition and sufficient for achieving completeness to add to all possible combinations that you like the tensor product between state observables and input observables, because that would suffice for guaranteeing completeness. Indeed, you can take additional columns in K for the unlifted state and input equal to 0, and you can take A and B equal to 0, and then you will have the tensor product representation embedded in here, and that's enough to guarantee completeness. How about the choice of observable functions? Well, there is good news. You can still work with your favorite observables. Some of the most encountered are kernel functions, which in this case become product kernel functions due to the tensor product, which remain a kernel, and you can utilize reproducing kernel Hilbert spaces to do kernel regression. And I have a paper in 2024 that shows how to do that if you're curious. And there are also other works that pursue this approach. You can use product deep neural networks, or you can use product Takens delay embeddings, the approach which is typically referred to as HAVOC, the Hankel alternative view of the Koopman operator. What's also nice is that under certain conditions, these classes of observables yield Ritz basis. For example, if you use universal kernels and quasi-random sampling methods like Halton or Sobolev, this suffices to guarantee that you obtain a Ritz basis. So the conditions that we develop in this work apply naturally to most popular choice of observable functions. Before I show the connection to the nonlinear fundamental lemma, I would just like to illustrate a little bit the completeness guarantees that we claim. And to do that, I propose to test different methods. So the method from Proctor that consider artificial autonomous dynamics by stacking the input and the state and applying the observable to this higher dimensional vector, and our own method. And the idea is to mostly compare the methods towards themselves. If you add more observables, if this parameterization is complete, then you would expect that the approximation error would improve. And the 1.2 in the title refers to the fact that we use the parameter mu in the van der Pol oscillator equal to 1.2, which is typically indicative of a more complex nonlinear behavior. So you see here we start with 500 observables in the XU space, and we have some approximation error that is relatively okay, maybe not the best, but it's decent. And then we are significantly increasing the number of observable functions to 25,000 ones. And what we see is that actually the approximation error remains largely on absolute value at the same order, and moreover, overall is a little bit getting worse due to numerical errors. So this does not seem to imply that this approach has completeness guarantees, which we now know it doesn't, because stacking these things together does not form a Ritz basis in the lifted space. For what kernel functions we used and all the details I refer to my ArXiv paper that will be mentioned at the end of the presentation. Now, we take also the approach that we developed in this paper, in this work, the generalized Koopman operator, and you see the difference here. We separately lift the states and the inputs, and we construct the Koopman operator that acts on the tensor product or the Katy-Rao product of the two data matrices. And what we see is that we start with 100 state observables and 50 observables. To begin with, already the approximation error is significantly better than in the previous approach, but that's not our main concern. What we would like to point out is that as we keep on increasing the number of state observable functions to 500 and 800, we consistently see that the approximation error is getting better, both in terms of absolute value and individual errors, which is a good sign and supports our theoretical proof of completeness. Also, we see that this shows that we scale much better than the previous method, because the total space obtained as the tensor product 50 times 800 is a 40,000 dimensional space, while in this case, in the previous case, we could not let's say go beyond 25,000 observables. In this case, where we sample the spaces separately, it's also, besides completeness, we also have better numerical scalability. One other observation that I would like to make, which I think it's interesting to know and connects to a wealth of methods that could directly be used to approximate the developed generalized Koopman operator, is that the so-called deep operator networks, the DeepONet, or the neural operators introduced by Chen and later further developed by Liu and others with the team of Professor Karniadakis from Brown University, are in fact can be shown to be equivalent with instances of product neural networks whose output linear layer provides an approximation of the generalized Koopman operator. And for this type of networks, you have many toolboxes or opportunities to use PyTorch to train them efficiently. And we see that the Koopman operator is in fact related to these coefficients that come in the output layer. The difference is that in these universal neural operators, the approximation problem is taken sequentially. So first there is a trunk network that encodes dependency, for example, on the state or on time, and then the coefficients in the output layer of this trunk network are used to embed the input functions, and that's the branch network. And then sequentially you end up to the product of the two networks, and you can take out this coefficient outside. While what we do in our work, we arrive at an end similar representation, but we basically, due to the isomorphism between the tensor product of L2 spaces and the L2 space defined on the Cartesian product of spaces, we basically can lift the state and the input separately. We don't have to do that sequentially, and we arrive at the same product of networks where the coefficients are directly outside the product. It's interesting to note that in the recent work by Guo and others, without apparently knowing about the neural operators by Chen and Chen, they arrive at a similar construction by treating U as the parameter of the Koopman operator, and they propose a neural network to encode K Koopman of U and a neural network to encode the state observables. But what they do actually, they are in a way rediscovering the neural operators within the context of the Koopman operator. Finally, I would like to make a connection between the generalized Koopman operator and the nonlinear fundamental lemma. And for the people who are not familiar with this terminology, I will make first an introduction. So initially, Igor Mesic has had a very nice survey paper and talk where he likes to emphasize that operator is the model. It is the most truthful representation of a dynamical system. And in the same time, we have in the Netherlands Jan Willems, whose opinion was that data is the model, so that data is the most unfalsified representation of the dynamical system. And this comes from the result that Jan Willems had, which is called the Willems fundamental lemma, and was originally developed for linear systems. And I explain this result now in a simplified case where we assume a linear system with state-dependent output, and we assume the state is available, and you can take trajectory of this system, so a bunch of initial conditions, x0 to xt, and you can take a sequence of inputs from u0 up to ut plus n minus 1, structured here in a so-called Hankel matrix, and then you can stack together the corresponding output sequences of this system. And what you can show is that if you multiply these trajectories, so the state, input, and output trajectories with a real vector g of compatible dimensions, then what you get at the output, so the interpolation of this trajectory, is also a trajectory of the system. Moreover, Jan Willems and his co-authors prove that all the span of this matrix coincides with the complete set of the solutions of this linear system under the condition that this matrix has full row rank, which corresponds to the persistency of excitation. And this is a very useful result because it shows that you don't even need to basically explicitly identify a model to predict or simulate new trajectories, but you can directly infer new trajectories of your systems directly from data. And of course, there is a very much growing interest into generalizing this result to nonlinear systems. And what I will show next is that the developed generalized Koopman operator theory gives us a nice way how to do that. So in order to generalize the fundamental lemma for linear systems to nonlinear systems, we first consider the same discrete time nonlinear system with the inputs and states and the equivalent Koopman model, where we add now additionally an lifted output, Wt, which corresponds of some observable functions that depend on the output, and they also must form a Ritz basis in the corresponding Hilbert space. And we introduce a new linear operator, calligraphic C, which basically extracts the lifted output from the lifted state. And we have the additional assumption that the state observable functions and the output observable functions are injective. And under this mild assumption, we have that a solution xt, ut, yt, where t belongs to the natural numbers, is a solution of the original nonlinear system if and only if the corresponding lifted states zt, inputs vt, and output wvt are a solution of the Koopman infinite dimensional system. And we see that this injectivity property is necessary for the if and only if statement. Under these assumptions, we can construct a similar system of equations where now you see in the top part we have the tensor product of the lifted states and inputs, which form the basis in the lifted space, and associated with each of them we have the stored lifted outputs, and we can prove that a trajectory of the lifted system necessarily satisfies this system of equations, which is represented only by data and the observable functions. And via the previous established equivalence, we can obtain a bidirectional relation, that is x, u, and y are a solution of the original linear system if and only if, for suitable observable functions, there exists a vector g such that the following system of equations is valid. So this is a new approach to the nonlinear fundamental lemma and can be used for simulating, for generating new trajectories, multi-step, or for designing predictive controllers without explicitly first identifying a model. Now, in conclusion to my talk, we have introduced product Hilbert spaces as a natural framework for generalizing the Koopman operator to system with inputs. Part of the novel contributions include we have derived a constructive proof that shows that the Koopman operator defined on tensor products of Hilbert spaces exists, and we have also shown that the assumptions that the state and input observable functions form Ritz bases and their corresponding L2 spaces, it's a necessary and sufficient condition for completeness. Also, we have shown that the developed architecture of the generalized Koopman operator yields a scalable family of data-driven approximation methods via singular value decomposition of Carteret-Rao tensor products. And finally, if universal kernels are used as observables, we can show that a decoder is not required. That is, the Koopman operator can map directly into the original state space X or output space Y. Further extensions are possible and will be presented in future work, like extensions to continuous time systems, interconnected systems, hybrid systems, and please stay tuned for future work. So I would like to thank you. If you are interested in the technical details, you can check out my arXiv paper on this topic. And I would like to acknowledge the great book written by Professor Yutaka Yamamoto from vector spaces to function spaces, which was of great help for me in deriving these results. Thank you very much. This concludes my presentation.